The next topic we're going to talk about is the sample variance and sample standard deviation. So what do you do if your data represents only a portion of a population? The formulas are close, are similar, but slightly different. All right, so next to the sample versions, I've written the population versions. And let's begin with sample variance. Instead of using the little Greek letter sigma, when we do samples, we tend to revert back to English letters. So we've got a lowercase s here. In the numerator, you'll see we're still going to sum up. We're going to take each piece of data and we're subtracting x bar. And keep in mind, x bar is the symbol for the sample mean. So when we compare that to the population version, which it looks like I wrote incorrectly, sorry, should be that. You can see the only thing that changed is the x bar, which is the sample mean, gets switched to mu, which is the population mean. The biggest difference comes here in the denominator. We have sample size lowercase n, and we subtract 1, whereas in the original formula, we just use capital N. The reason for that is complicated. You have to look at a whole lot of examples. But it does turn out that dividing by n-1 for a sample gives a more accurate estimate than if we just used little n. And it has to do with the fact that when you are including the sample mean in your calculation, remember a sample mean is an estimate of what the mean for the real population would be. So it's not guaranteed to be exact. And this -1 kind of helps minimize that error. In this formula, mu would be exact because we'd have all the population data. Comparing the two versions for standard deviation, again, it's essentially the same formula with the major difference being that we're going to divide by little n-1 instead of capital N. But essentially, you're practicing the same process. So I modified example 3 to look at only one data set. And this is a data set for a group of high school football players who had concussions. And that group was split into 2 groups based on the number of days it took them to recover. Players in the first group recovered in 14 days or less, so the rest were put in the other group. And we want to find the sample variance and standard deviation of their recovery times. So we're working with only a portion of the population, namely the portion that recovered in 14 days or less. Here's the time, which is being measured in days. And to calculate the variance and standard deviation, it starts by knowing what your mean is. So I need to sum up my pieces of data. And if you sum up these numbers, you get 90. So to calculate the mean, I'm going to take the sum of the pieces of data, and I will just divide by normal little n. Okay, the formula for mean does not change, only the variance and the standard deviation. So I'm going to take 90, my number of pieces of data, which is 12, and if you take 90 and divide it by 12, you get 7.5. Okay, that's 7.5 days. So now, to calculate the sample variance and sample standard deviation, I'm going to write my formula here because, again, this is actually how I compute these and know what to do next is by looking at my formula. So I'll show you how I do that. So when I look at this formula, I start in the inside of the parentheses and I say, oh yeah, I've got to calculate the deviation, the difference from the mean for each piece of data. So I'm going to begin by taking 4, subtracting the mean, which we know is 7.5, which gives me a negative 3.5. I'm going to continue doing that the whole way down the column. When we sum the deviations, it doesn't tell us anything. You can check and verify that it turns out to be 0. So the next thing the formula says to do is to square that and get that total. So we're going to take the previous column and square every entry. So I'm going to begin by taking negative 3.5, squaring it, which gives me 12.25, and continue doing that down the column. Now, a quick note about technology here. If you're using a calculator to assist you, as I assume you are, in squaring these numbers, when you have to square negative 3.5, do not just type it in the calculator like this, a negative sign, 3.5, and squared. It's going to do things in the incorrect order. What I really mean is take the whole number, negative 3.5, and square it. So when you put it into the calculator, you do need to put the negative 3.5 in parentheses. Okay, it's critical that you do that with any negative values. And of course, all of these numbers then should turn positive. So now when we sum them, we will actually get a number that's meaningful, not just zero. Turns out it becomes 39. So going back to my formula here, it says, okay, I'm going to take that sum, which is 39. I am going to divide it by my little n, which again, my number of pieces of data in my sample was 12. And I'm going to subtract 1 before doing that division. So I want to take the square root of 39 divided by 11. And again, you don't want to round before the end of the problem. So at this point, you'd want to put in square root, and then inside your square root symbol, put the 39 divided by 11. And we're going to round this off. Our pieces of data did not have any decimal places, so we can give 1 decimal place in our standard deviation. And if we round, this number originally looks like 1.8829, etc. If we round it to 1 decimal place, it is going to round off to 1.9 days. Now that's the standard deviation. Remember, the variance is just the portion underneath the square root. So the sample variance, which remember is s squared, is the same as 39 divided by 11, and giving 1 decimal place of that should be 3.5. So my sample variance is 3.5 days. Units are important. And my sample standard deviation is 1.9 days. The last thing we're going to take a look at in this section is what about if you actually have a frequency distribution? So it's kind of annoying, like in example 2 here, to list 41 3 times. If you have to list things that repeat each time that they repeat, your data set can be significant in size. We can shorten up our tables by writing a number that appears more than once, only 1 time, and recording its frequency next to it. But this does change our sample standard deviation calculation. Before you add up the individual variances squared, you're going to multiply it by that frequency. And if it happens that instead of having each piece of data and its frequency next to it, you have classes with a frequency next to it, you use the midpoint, as we've seen before, to be a representative member of that class. So I wanted to keep things short here. So example 8 is a data set having to do with the number of children per household. You can see the book for the full description. But what I want you to see is here we have been given a frequency distribution. There were 10 families in this sample that had no kids, 19 that had 1 kid, 7 that had 2 kids, and so forth. So what we're going to need to do here is, rather than totaling my x's, I will want to total my frequencies. And these numbers will add up to 50. So I have a total of 50 pieces of data. And in order to find the mean, I need to multiply each piece of data times its frequency so it's weighted appropriately. So that's why you see an x times f column here. So I'm going to take 0 times 10, which is 0, 1 times 19, etc. and I'm going to sum up this product column, and that'll be 91. So as we've seen before, the sample mean for a frequency distribution is the sum of those products divided by the sum of the frequencies, which is also known as our little n. So this is 91 divided by 50. I get 1.82. And it's preferable not to round that at this point. You, again, hold off rounding until the end of the problem so that you don't introduce errors. Now, I've brought down my formula. You can see the first thing I need is just the straight up variances. So I need to take each piece of data. So I'm looking at the X column and subtracting the mean of 1.82. So that makes the first one negative 1.82. I take 1, I subtract 1.82, and I get negative 0.82. I'm going to go down the whole column. Next, the formula says we're going to square our individual variances. So here you're going to go back to the previous column and square these numbers. So the first one should be 3.3124. Keep decimal places for accuracy, and continue going down the column. And the last thing I need to do before getting a sum is to multiply my last column of squared values times the frequency. So in this case, you want to make sure that you're looking at the right two columns. I am multiplying this column, which I'm highlighting in yellow over the blue, times the frequency column, this one over here. So if we multiply 10 times this decimal, that will become 33.1240. Continue going down the column, multiplying. All right, according to the formula that I'm following, I should now sum these up. Turns out to be 145.38. All right, now if I want the sample variance, remember that's the same formula but without the square root. So I will take 145.38 and I'll divide by, remember, don't just use n, use n minus 1. So my number of pieces of data, remember, don't just look at the table and think there's 7. Remember, you have to add up all the frequencies. So the number of pieces of data here is 50. So I'm going to end up dividing by 50, take away 1, or in other words, 49. So I will take 145.38, divide by 49, and that is going to give me a sample variance of approximately, we would go to 1 decimal place, 3.0. But again, what's more important is that we get the standard deviation, and don't just take the square root of this 3.0. Make sure you use the fraction so that you're keeping all the decimal places. So you're going to do square root of 145.38 divided by 49. And that gives you the decimal 1.722. So if we're going to approximate to 1 decimal place, that's going to be 1.7. And again, this represented a number of children per household. All right, now example 9, the last example, covers what do you do if you have classes with frequencies. So instead of having individual pieces of data with their frequencies, I just have counts. I have 380 pieces of data in this case that are in the class from 0 to 99. You can see the book for the data set and the full solution. I'm not going to go all the way through this one because the numbers are just gigantic by the end of it, and it's just a mess. But I want to talk through the basic idea with you. So this ended up being how much individuals spend in preparation for personal travel each year. Okay? So what you're going to do in this case is you need to have an x value to multiply the frequency by. So remember, the way we get our representative piece of data for a class is to find the midpoint of the class. So in this first instance, you're going to take 0 and add 99, divide it by 2, and you'll get 49.5. And that's going to be your representative piece of data for this class. You would continue finding the midpoint of each class the same way. Now, there is one wrinkle here at the end. You can see there's a category for people who spend more than $500. So if I'm trying to find the midpoint, I don't have an upper value here to average with the 500. So you're supposed to choose a value to represent the midpoint, keeping in mind numbers could go as high as 600, 700, 800. So your textbook suggests using 599.5. I guess assuming that people don't go ridiculously crazy and there's a lot of people who are, spending $1,000 on travel. But this is an estimate, so that does introduce some error into the process. But once you've gotten through that, then basically you can ignore the classes. And now this table looks just like the last one we did with an X and F, product of X and F, etc. So once you have gotten the midpoints, you'll do the exact same process as we saw in the last example to get the answer. So again, that's why I'm not going to take you through the whole thing, because after the first step of finding X, the midpoint, it's the same as the last one. And all the work is fully shown in the book if you do want to see.